Thanks everyone to join us for this deep learning session. The first talk is given by James Jordan on the paper Rayard-GAN, leveraging multi-data sets to improve target-specific predictive model using GANs.
Okay, yeah, so hi there. So I'm presenting this paper today. I'm James Jordan. This paper was written together with my colleague Jinsung Yoon from the University of California, Los Angeles. I'm from the University of Oxford, and we're both supervised by Professor Mihaela Vandershaw. Yeah, so the problem we're looking at today is that machine learning methods in general require large amounts of data to train them well. And a key observation we make is that machine learning methods perform best when we train them on the data when trained on the target distribution in which we wish to deploy these methods. And often the target distribution, the target deployment data set may have very few samples. The solution we're coming up with here in this talk is to use auxiliary data from additional data sets from related sources to generate synthetic data to enlarge the target data set. And so what that might look like is a concrete example of this is suppose we have multiple hospitals in which we wish to deploy a predictive model. There may be few samples that are relevant to the predictive model in any individual hospital. For example, in hospital A here, the number of samples may be quite small, and so any predictive model that we train on this data set may have poor performance. However, in hospital B, we have many more samples, and so the performance is better. But what we can do is we can try and use all of these hospitals together to try and leverage the data that we have from multiple sources to improve the prediction performance across all hospitals uniformly. So there are two key challenges to this problem. The first is distribution mismatch, and it's that two different hospitals may have data distributed in different ways. So, for example, it could be that the age distribution in a certain hospital is different to another, or that the gender distribution is different. And this is important because when we train predictive models on distributions that are different, it's been observed that the performance is hindered by the fact that the training and test distributions are different. The second challenge we face is feature mismatch, and that's that different data collectors, different hospitals, measure different features for different things. So for example, one hospital may conduct a certain set of lab tests and another hospital may conduct a different set of lab tests. And this is certainly the case. For example, the lab tests conducted for different diseases in the UK are different to the lab tests conducted for the same diseases, but in America. And this is a key challenge in using the additional features that are measured in the different hospitals. We don't just want to discard them. We want to see if there's some way in which we can leverage the additional information found in the extra features. So what our approach is we use multiple GAN architectures to translate the data from one data set to another. The distribution mismatch here is dealt with by the adversarial framework by introducing discriminators for each of the different data sets, ensuring that the data that we map from the other data sets into this target domain matches the distribution of the original target data. The feature mismatch is addressed by introducing a latent space Z through which we map all of the data, and so the shared representations exist in this latent space Z, and the problem of feature mismatch is dealt with in this way. So I'm going to talk a bit about the motivation behind our idea here. And the intuition is that distributions with similar shapes, which we don't go into any technical detail of in the paper, but this is simply intuition, is that it's easier to map distributions from one distribution to another if they have a similar shape. The expectation is that data from related sources, such as data from two hospitals, data from different medical studies on the same disease, data from any two related sources are likely to have a similar shape to the target data we're trying to map to. And the idea here is that rather than use random, so in the GAN framework, they use random noise as the input to generate additional samples, if you like. We're going to replace that random noise with the auxiliary data from the target hospitals. And so according to this intuition, we ran a couple of experiments. And so you'll see here, what we've got is that the top row is showing the what happens when we try to map a Gaussian distribution to another Gaussian distribution with the translated mean. And you see that naturally the linear model does quite well already. One-layer perceptron and two-layer perceptrons also will do perfectly fine. However, when we try to map a uniform distribution to a Gaussian distribution, what you can see happens is naturally the linear model doesn't do very well at all, but even the slightly increased flexibility of the one-layer and the two-layer perceptron still don't quite capture the mapping very well. And we conduct another experiment in which now we're looking at translating from a single-mode Gaussian to a five-modal Gaussian and a four-modal Gaussian to a five-modal Gaussian. And as we go across from left to right, we increase the number of samples we have of the target data. And you can see that as the number of samples increase, it's easier sooner, if you like, to map from 4 modes to 5 modes than it is from 1 mode to 5 modes. And this is sort of the intuition behind what we're trying to do, is that if we use the auxiliary hospital or the auxiliary data to map into the target data, it's going to be easier than if we just tried to generate extra samples using random noise. So there's a few related works in this area. Perhaps the most related to ours is the paper by Wiens, Getag, and Horvitz, in which they address the problem in the medical setting like us, but they only address the problem of feature mismatch among hospitals. And they do it in a somewhat naive way by simply concatenating the vectors and discarding any features that don't exist in the target hospital from the auxiliary hospitals. And like I said at the beginning, what we'd like to do is avoid discarding any information that we have about the data. They fit a simple logistic regression model on top. CycleGAN is somewhat most architecturally similar to our work. However, they don't introduce a latent space. What the CycleGAN architecture would do is learn pairwise mappings between any two hospitals. It deals with feature mismatch. It deals with distribution mismatch. What it doesn't do, though, is it doesn't map through the latent space, and therefore it doesn't share the learning across different translations. So when we pair hospitals 1 and 2, the data from hospitals 1 and 2 is only used to train that network. Whereas in our framework, what we do is we pair all hospitals, we group all hospitals together, and the translation that is learned from hospitals 2 to 1 is influenced by data in hospitals 3, 4, and 5. You can also see across the bottom there that the number of networks required in a CycleGAN is on the order m squared, whereas you can see our method is linear in m. And so the number of parameters is much smaller, and so the amount of data we need to train our networks is much smaller. And this is because of the shared learning that I was just mentioning. The final related work I'm going to mention is StarGAN, in which they would learn a single neural network to translate between any pair of data sets. The problem there is that obviously the input is of fixed dimension, the output is of fixed dimension, and so the problem of feature mismatch isn't naturally addressed. They do have shared learning, but in this case they only have one network, and the flexibility there to be able to learn the potentially different mappings from, say, hospital A to hospital B and from hospital A to hospital C isn't there because they're only using a single network, and there's only a single input changed when they were trying to learn, if they tried to learn the different mappings. So our model, we introduce some encoders, FI, that map from the spaces xi cross y, where xi is the label space, is the feature space for hospital I, and y is the common label space. Maps it into the latent space, and then we decode those mappings using some decoders, which we label GI, mapping from the latent space into the feature and label space of the corresponding target hospital. And finally, we have the discriminators, which I talked about earlier, which are going to attempt to distinguish which samples came from the target distribution, which ones were mapped through these encoders and decoders to get to the target domain. And ultimately, the goal of this, which you set in this paper, is to learn predictors for each of the hospitals on each of the feature label pairs. And the idea here is that we're going to learn the predictor for hospital 1, say, using hospitals 1's data and all of the translated data from hospitals 2 through 5. So more concretely, the losses are on the screen there. The adversarial loss is sort of the standard adversarial loss you see in the GAN framework, where the generator now is sort of a combination of both encoder and decoder pairs. The cycle consistency loss is something that's introduced in CycleGAN, which ensures that when you encode and decode, you get the same thing back, or conversely, if you decode and encode, you get something the same back. And so we optimize these losses in the standard minimax way that's done in GAN, using lambda as a hyperparameter to trade off between the two losses. So the experiments we run are on a data set called MAGIC, which we're very grateful to have, which is a collection of 30 different data sets from 30 different medical studies. So naturally, it's a great candidate for this kind of work. We use the 14 studies that each contain at least 500 patients. This allows us to have a testing set of a significant size to allow us to do meaningful tests on this. But we only ever use 500 patients in the training. So what I'm saying by that is that we are still restricting ourselves to small data sets in the training section, and we test on the remaining patients. The label in the data set is the 1-year all-cause mortality. The number of features across all studies together is 216. The average number of features is 66, and the average number of shared features is 35. So it's actually quite low, and it's not a simple task to ensure that the features are mapped between each other correctly. So obviously we compare with the benchmarks I mentioned earlier, but we also compare with some common sense benchmarks. Target only uses simply the data from the target distribution, target domain to learn the predictive model and train it. Simple combine is the naive approach in which you take the union of all feature spaces and simply treat any feature that wasn't measured in your given hospital as missing, so set it to some predefined value. And obviously this doesn't deal with the problem of distribution mismatch. Then we use a conditional GAN framework to generate additional samples. Now this still only uses the target only data, and what we do is we simply, conditional on the label, try to generate additional samples. And this is sort of like the idea behind this is to check whether the GAN framework alone is enough to improve prediction performance in this setting, and we'll find that it certainly can be, but isn't always. CycleGAN, as I explained, StarGAN and Means et al. The metric we use, what you'll see in the next slide, is the AURC and the AUPRC improvement over using the target-only benchmark. So what we see in this slide is that radial GAN does outperform all of the benchmarks. In fact, we can see, somewhat surprisingly perhaps, that one of the papers that's supposed to directly address this issue, Means et al., in fact, negatively hinders the performance across all of the tests we ran. And so these tests are ran with M equals 3, 5, and 7 hospitals, or data sets rather. In this next slide, we have the improvement over baseline, but now we're learning on all 14 available data sets, and you can see that in almost all cases, radial GAN improves the performance, and in some cases, it significantly improves the performance, whereas most of the methods, certainly, for example, Means et al., doesn't improve the performance much at all, if ever. And so in this one, we're looking at the random forest being the predictive model that we built on top of our translated data sets, and this slide, we're looking at a neural net as the predictive model built on top of our slides, and you can, on top of our translated data sets, and you can see that both models, both the random forest and the multi-layer perceptron, in most cases we have a performance improvement over simple combine and target only and all the rest of the benchmarks. And so the final experiment we ran is sort of a sanity check, if you like. The two graphs you see here are the AURC and AUPRC of our performance, and the yellow line indicates our performance, and the blue line indicates the baseline if we just had the fixed 500 samples baseline. And what the orange line represents is if we'd simply taken more samples from the real data. As you'd expect, this is the best we can possibly do. We can't hope to generate synthetic samples that improve performance better than just getting real samples. That's what you'd, sort of the gold standard of synthetic samples is something that does as well as this. And as you can see, our yellow line from radial GAN very closely follows this curve from getting extra real samples. And so this is a very good indication that radial GAN is generating synthetic samples that are meaningful. Thank you. Our post session is tonight in Hall B. If you have any questions, then there's a contact email up there. We also have a few other posters from our group, so please, those as well are on the screen. If you have any questions, please ask.
We have time for a few questions. There is a microphone here, so you have to stand there to ask your questions. So I have a question for you.
Yep.
How do you decide if a data set should be included?
So currently, that's more an intuition than anything else. Like we said at the start, the intuition behind the whole thing is that we're trying to select data sets that we believe to have similar shapes, which we haven't formalized in the paper, but that is certainly a future work we'd like to look into, in which we formalize what we exactly mean by shape and what we mean, and use that framework to build on and decide on which data sets should or should not be included.
Have you tried with, like, when you have one data set which has nothing to do with all the others to see if that degrades your performance?
No, that's not a test we perform, but that would actually be an interesting test. So, yeah. I suspect, though, that it would. I mean, so the intuition being that the data sets have similar shapes, certainly there could be data sets out there that spuriously have the same shape as whatever target data set we have. And I think this method should be deployed essentially with common sense, with the idea that you know, we're expecting performance improvement because we're using data sets that are from related sources. The other thing I'd say is that I suspect it's difficult to actually say whether a data set should or should not be included. Because if you could say that, then you're implying knowledge you have above about the target data set that you maybe don't have. The whole point of including extra data sets is to introduce information and knowledge about the target domain that you otherwise wouldn't have. So if you could quantify the information you didn't have, that seems odd to me, if that makes sense.
If there is no other question, let's thank. Oh, there is a microphone here if you want to ask the question.
There's one there, I think.
Oh, sorry, I didn't saw the Paul staying there.
Hi,
Okay.
I wanted to ask whether you've tried to compare the predicted missing features to something. Like you're saying that some of the data sets are contain features that others don't.
Yeah.
Have you looked into what those predicted features are and whether that information is actually useful?
So what I think you're asking is, so what we do is we don't predict features in the sense that we don't take a sample and then look at which features are missing and then sort of impute them, if you like, or predict them on top of the original sample. We take the entire vector of features, map it into the latent space, perhaps deforming it in some way, and map it back out into the other space. And it's not that the shared features, for example, may not be the same when we map it out into the target space, but the idea is that the distribution as a whole has been mapped through these encoders and decoders and comes out as a whole similar to the target distribution. I hope that answers your question.
Yeah.
Thank you for your talk. One of the big problems in classification that we have is imbalance problem. So for example, we have a binary classification problem and one class is extremely rare. What we usually do, we do like oversampling, undersampling, generating synthetic data points of rare class, but in a very stupid manner. So what I was thinking right now during your talk, did you try to use your method in order to generate synthetic points, but not for the whole data set, but for particular class, in order to improve performance of classifiers in imbalance settings?
So that's not something that we tried, but it's certainly an interesting question. I guess, yeah, I mean, it's certainly a feasible idea. And what we did actually do with the paper that we did condition on the label. And so every sample we generated was conditioned on the label. And you could, in theory, use that to oversample and generate points that way if you liked. I guess what this method does is it generates more points of more of every point, and you could simply subsample that once you've done that, and that would be a natural thing.
It seems to be a very natural continuation of your idea. It could really
definitely.
work.
Good question.
Thank you.
So we have time for one last quick question, and if the next speaker can stand, let's come to the...
I'd like to ask what's the data set? There's the text or image, and how you deal with the data sets.
Sorry, could you repeat that?
What is the data set? There's the image or text, or mix of
Oh,
them?
so it's medical data sets. So it's patient features are like blood pressure, heart rate, various medical tests, age, height, gender.
Yeah. How do you process the data sets to how say push them into the GAN network?
Yeah. So most of them are already numerical, and then we encode the binary features in other ways, like natural ways to encode the binary features. Yeah. So if you want more details, come to the poster session.
Yeah. Thank you.
Let's thank the speaker again. So the next speaker is Konstantinos Kamnistas, and he's going to present his work called Semi-Supervised Learning via Compact Latent Space Clustering.
Hello everyone, I am Kostas, fourth year PhD student in Imperial College London, and I'll be presenting you the work that I did as an intern in Microsoft Research. We know about supervised learning. You have some labeled data in your hand, you learn a decision boundary. In semi-supervised learning, you also assume that you have some unlabeled data. Quite often they are more than the labeled data, and you hope that you can extract information from them basically that will help you learn a decision boundary that generalizes better. And the way that SSL methods do that, SSL for semi-supervised learning, they often assume that the so-called cluster assumption that basically that points that belong to the same cluster in the feature space where we are performing our classification, they should belong to the same class, which also translates basically that the decision boundary should lie in low density regions. In our work, what we are interested in is basically to learn a latent space that facilitates class separation, and we're going to learn it with a neural network. But to do that, we're going to enforce a further constraint. We're going to enforce that every sample that belongs to a class, all of them of the same class, should form a single compact cluster in the feature space. And we're going to do this, we're going to enforce this by creating dynamically a graph at every iteration of SGD, basically to capture the structure of the manifold in the latent space of the neural network. We're going to apply a label propagation, which is a method that I'm going to show on the graph to basically capture the arrangement of the clusters in the latent space. And then I'm going to introduce basically a cost function that is going to regularize the shape of the graph in order to form compact clusters in the latent space that will facilitate basically the classification even by a simple linear classifier. To position our work basically in comparison with existing literature, I will start with graph-based methods which are the most relevant to us, especially label propagation that we are going to apply, and the local and global consistency method, which is actually very, very similar in nature. I think the two were derived more or less at the same time in parallel. They both require a pre-constructed graph in hand, and given that, they basically do transductive inference. They propagate labels along the high-density regions of the space. And the very beautiful thing about this is that these authors actually showed that there is a closed-form solution for label propagation, which is very easy to compute. We're going to use label propagation, as I said, but to regularize an inductive classifier. And the thing is, transductive inference is a little bit inconvenient because you need all the samples in your hands to basically perform inference. Other methods have tried to use graphs to regularize inductive methods. For example, if you are given a graph, a pre-constructed graph that expresses the similarity of some samples, and for example, it's appropriate that on the graph the clusters are kind of separated, you can regularize a method that in the latent space also it preserves these similarities. There is pairwise similarities, and so in the latent space the classes will be also separable. But it's not easy at various tasks to construct yourself such a graph. And we're going to basically learn one instead. One method that also did this recently that does not require a graph is basically looking for association cycles going from a labeled sample to an unlabeled sample and back to labeled. And basically this formulation, what it does essentially is it attracts unlabeled samples to the closer labeled sample. It doesn't really capture the whole structure of the manifold that we're going to focus on. Another popular approach for semi-supervision is the self-supervision, which basically it says you make a prediction for every unlabeled sample, and if this prediction is confident, you're basically putting this unlabeled sample together with the prediction in the training set, and you're continuing the training. And it's very relevant to the very well-known entropy minimization regularizer, And it's very relevant because the latter, basically, you can see it as if the prediction of your model is actually the target for your model. Both of them, what they do is they encourage confident predictions, which pushes basically samples away from the decision boundary to be confident, to lower the entropy. But they induce the so-called confirmation bias, which basically means if you are making a mistake, if your classifier is making a mistake, you're encouraging it to be a confident mistake, and so amplified, basically, which our method is going to try to avoid. Another type of approaches is those that encourage consistency under perturbation, which means basically you take the unlabeled sample, you apply a little bit of a noise in the feature space, you move it a little bit around, and you encourage your method to be giving consistent prediction regardless of the noise, which is also pushing away basically the samples away from the boundaries, because away from the boundaries, the prediction doesn't change. So it is subject to confirmation bias again. And the other thing with this is these methods basically focus on encouraging local smoothness of the predictor around its samples through the perturbations, while our method is completely orthogonal to this. As I said, we're going to focus on capturing basically the whole manifold structure. And finally, very quickly, the generative models, where basically these methods try basically to model the whole generative process that creates the data X, which is a far broader and a difficult problem than simply modeling the classification task. And usually these methods tend to be to use more complex models, such as the required generator, the GANs and device, and the autoencoders, etc. While our method is a simple cost function, basically tailored for the semi-supervised learning task. Now that we have positioned our work, I'll go back to it in detail. As I said, we're going to focus basically on the latent space zeta, that is at the last layer basically of the network right before the linear classifier, and we're going to regularize it to form compact clusters in there. Basically, we're going to regularize the feature extractor of the network. We are not going to touch essentially the linear classifier at all. It's going to be trained at the same time, but with standard supervision on the labeled samples. We're going to focus on the latent. And we are working within the framework of training a neural net with absolutely standardized GD, but at every iteration we are creating a batch that has both samples from the labeled and the unlabeled data, and we plug them through the network and we get the embedding in the latent space out. And we're going to look at this one and we want to capture basically the manifold there. How? We create dynamically at every SGD iteration a graph over those samples of the batch. And in practice, it's very easy. Basically, all you do is you compute an affinity matrix like this after having chosen your similarity metric of preference. A very important bit here is that we also compute basically the random walk transition matrix, H, and it's very important to understand what it says because we're going to use it a lot in the method. Basically, every element of it expresses the probability that if a random walker is on node I, the probability that it's going to transit to node J, which is going to be high if the two are actually close and 0 if they are far. And the next step is we want to basically estimate in the current iteration, the arrangement of clusters in the space. And we're going to do this by applying label propagation that I talked about previously on this graph. And the class posteriors will be informative. And it's very easy because the closed form solution that you saw down there that I showed you the authors of the other works have shown is actually very easy to compute via the transition matrix and the ground truth labels. Something that we noticed in this work and is very important is that actually this closed form solution is very simple and it's differentiable. And this enabled us to basically, in the next steps, to basically use these class posteriors to derive basically a cost function that we're going to minimize, backpropagate through the label propagation, through the graph, back to the feature extractor and regularize the feature extractor. Now, having estimated, as I said, the current arrangement of the clusters in the latent space, what we're going to do is we're going to regularize it to form a single compact cluster per class. And we're going to do this by basically encouraging the current transition matrix, H, to look as the transition matrix should look like in this desired state. And this desired state where compact clusters would be formed, like every sample basically would have a uniform probability of transiting to any sample of its own class and 0 otherwise. And we derive a soft target matrix for to encode basically such a relationship, that is the matrix T, and we derive it via the label propagation estimates, phi, where we can understand more if I show you basically the values that it takes, this target matrix takes for the binary classification case for two nodes, phi I and phi j. Yeah, essentially, if the class posteriors of label propagation match, the T is going to take a high value. If they don't match at all, it's going to take 0, basically. And using that, we're going to basically use a cross-entropy term that says that H should start looking as T, okay? As the current transition matrix look like the target matrix. And essentially what it's going to do is going to attract basically samples that the label propagation estimates match, and it's going to repulse the ones that the estimates don't. And unconfident samples will be in between. Here, before we will start investigating basically the effect of our cost function. And to do that, we're going to create some a synthetic latent space, 2D latent space. And place on it ourselves in an arrangement like the 2 moons that you see here, synthetic embeddings of samples. There is no feature extractor. And the reason is because I want to isolate basically the effect of the cost function and how it's going to try to change the embedding space. We're going to put a linear classifier on top. We are going to do the forward pass through a linear classifier, compute the classification cost, apply label propagation, compute the graph, compute our own cost, and back propagate through. The important point is we're going to compute the gradients of the cost with respect to the coordinates of the embeddings of the samples in the latent space, and we're going to apply the gradients ourselves to the samples to move them around the embedding space to basically see what happens. And in that case, what you'll see is, for example, the cost that we just derived, it's trying to move basically the samples in the space such that it will form some compact clusters. But the problem is, on its way there, it broke the structure, basically, the clusters, which basically translates in information loss. The structure in the manifold actually is enabling the cluster assumption, which enables the label propagation, and basically the behavior here gets bad because we're breaking the structure. So we have to fix this. So our idea is that instead of optimizing transitions straight from node I to J, we could be optimizing transitions along the shape of the cluster. And we can model this with a Markov chain. Now, what we know is that if I take the transition matrix H of the graph and multiply it with itself S times, what I get is the probability of jumping in S steps from I to J, but via any Markov chains that can be, any paths that can be even jumping across classes, and I don't want that. What we are going to model is the probability that we go from a sample I to a sample J via intermediate nodes that are only of the same class. And we are going to estimate this not by multiplying H by itself S times, but by masking the intermediate steps-based transitions basically with a soft mask M, which is a matrix that we derive that is basically expressing the confidence that every element expressing the confidence that node I and J are of the same class. And we compute it basically by taking the dot product of the posteriors of label propagation. It's going to be 0 if they don't match, 1 if they match, and anywhere in between. And we are using this basically to create, again, a cross-entropy like we said before, to optimize this multi-step transition matrix H, parentheses S, to look like the target matrix that we derived before for this desired state. So essentially, we're going to make all the Markov chains that transit to classes, to other classes 0, their probability, and we're going to attract nodes across Markov chains if their classes match. The final touch is basically that we are optimizing over chains of different lengths so that we penalize basically the case of leaving the cluster at the last transition at different steps. And this is essentially the final form of the regularizer that we derived, that is the CCLP, compact clustering via label propagation. I'm extremely creative with names. Going back to the 2 moons, applying now this new cost function that optimizes across Markov chains, what we see is that we get gradients that are nicely ordered, and follow along the shape of the clusters, and we do arrive at the compact clustered state while preserving these structures. Another toy example is this of the two circles, where first I will show you how another regularizer behaves here. It's the entropy minimizer, where it has suboptimal behavior here. Because as I said, it's a subject to confirmation bias. It basically pushes the samples away from the decision boundary to minimize the entropy. Our method in comparison, it's completely agnostic about the classifier. It doesn't even use the linear classifier on top. Its gradients only have to do with the geometry of the manifold. So basically, it avoids this problem. Now, I go on with the benchmarking that we did on MNIST, SVHN, and CIFAR, where this table is a little bit massive, and I'm going to walk you through. For every benchmark, basically, there are 3 columns. The first one on the left is the setting where we are applying semi-supervised learning with limited training labels. The next one is semi-supervised learning with all available labels used for training. And the third one is basically the standard pure supervision with all the labels. This is something like the standard thing that you see in non-SSL works. And down here, basically on the lower part of the table, I have separated basically some works that work with bigger networks, so they are not as easily comparable. What we see is that our method across all the settings is actually doing very comparable with the state of the art, regardless explicitly. It's just a cost function. Perhaps I would say the one method that outperforms us quite some in 2 out of 3 settings is the BatGAN, which is a recent method, which is a very, very good work, but it's a very complex system. It has 2 different networks in there, and I think 4 different regularizers, which supports basically that actually our cost function is actually pretty useful. The other very interesting result is that we saw that our regularizer, with basically doing encouraging compact clustering in the latent space, improves even the case where all the training labels are used, further than the applying the pure supervision with all the labels, which is very useful because it basically tells us that we can be using this regularizer in the common standard fully supervised systems that we have currently. And finally, an ablation study that we did where we were in, again, the same benchmarks in different settings, but we changed the metaparameter S, which is the maximum length of the Markov chains that we are optimizing over to check basically its effect. And what I show you again at every benchmark, the left axis and the blue line are showing basically the setting where you are using SSL, yes, CCL, our method, but with limited labels. And the right axis and the red line is when we are using all the labels, just to check all the settings, right? What I also show you here is the performance when we are not using semi-supervised learning and just fully supervised on these settings. And what we see is that in all settings, even when we are just optimizing with only one-step transitions, so we don't care about preserving the structure, all we care about is just enforcing compact clustering, we already get very big gains from, in comparison to no SSL, which basically supports the value of the compact clustering as regularizer. And then we also see that for optimizing basically along longer chains, it actually reduces the error further as long as you don't overdo it, you don't create too massive, too long chains. My final slide, the take-home messages. What we have shown is that this compact clustering state in the latent space seems to be improving generalization according to our experience. Optimizing while trying to preserve existing structures seems also to be beneficial. And I got to know graphs through this work, and they are beautiful if you want to capture structure. And what we saw is that you can actually create them dynamically at every batch of HCD to actually regularize inductive neural networks by capturing relationships between samples. Our method is a simple cost function, efficient and effective, and can be applied even in fully standard supervised learning systems to regularize them further. And for future work, what I am trying to do is analyze further, basically, especially theoretically, the properties of space compact that encourages compact clustering, and to use it in the unsupervised domain adaptation task. That's it from me. Thank you very much. Anything you want in the evening, I'll be happy to discuss. Thank you.
We don't have time for questions, so if the next speaker can come in.
I thought I did fast.
Well done. Good luck. Thank you. Oops.
All right, so the next talk is by Marta Garnello. It's about conditional neural processes.
Okay, hello everyone. My name is Marta, and I am going to be talking about conditional neural processes, which is joint work with all these other awesome researchers at DeepMind. So conditional neural processes can be motivated from lots of different angles, but the one that I find the most intuitive is to think about it in a few-shot learning point of view. Few-shot learning is this growing area of machine learning. It's related to meta-learning, and it deals with models that are flexible and they can adapt at test time. And that, to me, feels like an important property for intelligent systems. So what is so special about few-shot learning? When we compare it to traditional learning, if we look at the classic image classification task, normally any image of a dog is always going to have the label dog, and a picture of a cat is always going to have the label cat. This is not the case for few-shot learning. Here, in every episode, we're going to sample a subset of the images, we're going to give them some random labels, and then in the next iteration, we're going to throw those away, sample a different subset of images, and give different labels. And what you can see, what happens sometimes is that the same image can actually have different labels across the different episodes. To make this difference more clear, if we look at the underlying mapping from images to labels, the distribution is always the same for traditional learning methods, whereas for few-shot learning, this distribution is changing across episodes. So what this boils down to for me is the difference between having models that learn a single underlying functions from observing several observations during training to systems that can learn a whole distribution over functions by seeing different functions at every episode. And then at test time, what these models do is try to narrow down what this current function is by seeing a few context observations. Now, we want to learn the latter. We want a model that is able to regress distributions over functions. Let's look at what regression algorithms we have out there. Most famously, we know everyone knows neural networks. Neural networks are initialized at random, as you can see. And then during training, they observe tons and tons of training data, and their parameters get updated to regress this underlying ground truth function. During inference or test time, these parameters are fixed, and we hope that they will generalize well enough to our new target position. What's really neat about neural networks is that they learn all of this regression from data themselves. In addition, they can regress pretty complex functions because there's a lot of parameters that we can tune, and the evaluation at test time is really, really quick. It's just a forward pass. A different set of regression algorithms that is very famous as well are Gaussian processes. Now, assuming you know the underlying kernel and their parameters, GPs don't really involve any training. They're going to have some prior over the distribution over functions, and then at inference time, it's going to take in some observations and narrow down its beliefs over what the underlying ground truth function is. What's really cool about GPs is the fact that they are actually learning this distribution over function that I mentioned earlier, and in addition, they have this uncertainty over their predictions given the observations, and this is something that's also very useful for applications of machine learning. Now, we are introducing neural processes, which we aim to have a combination of both benefits. We're going to implement them as neural networks, so they're going to be initialized at random themselves, but they're going to model a distribution over functions. During training, our model is going to be exposed to a distribution over function, not just a single one, and it's going to learn some implicit prior over what our data distribution looks like. At inference time, we're going to give our model a certain observations point, and it has to narrow down its belief over what the underlying function is. And this is also going to be very fast because it's a neural network, so it's only going to be a forward pass. So how does our model work? Imagine we have this underlying ground truth function. And now let's assume we don't know what this function looks like. All we're given is a few context points, as you can see. And in addition, we're giving a target point x, which is where we want to predict our value function at, given the context points. What we're going to do is we're going to take those pairs of coordinates, we're going to pass them individually through an encoder to obtain this individual representations R. We're going to take all of these representations, we're going to aggregate them together to obtain our main representation R. Now R is going to capture all the information we have about the current function given the observations. We can use R in combination with our target, pass it through a decoder, and this decoder is going to output a mean prediction as well as a measure of its uncertainty over this mean prediction. Now in this example, I've only picked a single target, but once you've calculated R, you can actually choose arbitrary number of target positions and actually pass them through in parallel, which also makes this algorithm computationally quite good, as it's going to take a runtime that is linear rather than quadratic. In order to train this algorithm, we're going to pick a random function, we're going to select a random subset of points as our context points, and a random subset of points as our targets. We're going to pass the context points through the model, the way I described to you earlier, and have it predict the mean and the variance at the target positions. We're then going to use this mean and variance to calculate the log likelihood of the ground truth data and use that to update our model. Crucially, we're not going to do this on a single function, but every single time step, we're going to pick a different function with a different subset of points from our data set of functions. What this does is that our model is now forced to not just collapse to a single function that it overfits, but actually learn this whole distribution over functions. And it learns to use the context points at test time in order to infer the function. Now, what does our trained model look like? Here you can see the black line is the ground truth, and blue is our model's predicted mean and variance given the context points, which are those black dots. As we increase the number of black dots, you can see the model's prediction comes closer to the ground truth, and the variance is also reduced, which is interesting. Now, what's really cool about conditional neural processes is that if you have enough data, they can learn really complex implicit kernels. So rather than just trying it out on Gaussian curves generating by a GP, we'd like to move on to a bit more of a complex regression task. And what we chose are images as complex functions that we can try to regress. The way this works is we pick a pixel position, and that's going to be our x value, and then the color of that pixel is going to be our y value. So as a context, I'm going to give you a couple of x positions across the image with their color. I'm going to ask, what's the color at this other position given that context? We can also ask for the pixels, for all the pixels in the image, and basically reconstruct the entire image given that context. And this is what we did, and you can see that as the number of context points increases, the accurate mean prediction of our model gets better and closer to the ground truth, and the variance is reduced. You can see that already with very few context points, even just one, it already has some sort of implicit prior over faces, and it already generates this average of a human face with that face color of the 1 pixel. You can see that our model performs really well, also compared to other models, particularly with few context points. Now, this does not mean that CNPs are better regressors than GPs. It really doesn't. This is more of a trade-off. If you know the kernel and you have the parameters, a GP is probably a very good choice. If, however, your kernel is very difficult to describe and you have lots of data that you can use, then CNP is probably a very good option. Finally, we also wanted to test our model on classification and show that this training regime goes beyond just regression. So we applied it to few-shot classification using the exact same model and achieved results that are on par with state-of-the-art algorithms. Finally, I'd like to advertise follow-up work that we did on neural processes that we're going to be presenting at a workshop on Saturday. So far, I've only shown you the mean predictions of our model, but now imagine you want to actually generate different samples from that model using that variance that we actually have. At the moment, what it would look like is like this, because as I told you, these variances are sampled independently from each other, so they cannot talk to each other. If instead we actually wanted to have coherent images every time we sample, what we're going to do is introduce a latent variable that gives global information across our entire model, and then we're able to actually generate consistent samples. And we're going to be talking about this in the Deep Generative Model workshop on Saturday, so if you think this is interesting, then please drop by as well. I'd like to thank all my great collaborators once again, and I hope to see you tonight, poster 130. Thank you.
again, we don't have time for questions, so thanks the speaker again. And can the next speakers come? All right. So the next speaker is Tal Friedman, and he's going to talk about a semantic loss function for deep learning with symbolic knowledge.
Okay. Hi, everyone. I'm Tal. I'm presenting this work. This was work done jointly in the STAR AI lab at UCLA. Okay, so our goal here is we want to constrain the outputs of a neural network using propositional logic. So I want to be able to, given a sentence in logic that describes what the relationship is between the outputs of a network, I want to be able to incorporate that into the training process of my network, along with my normal training data. Ideally, I'd like to be able to do it without changing very much about the training procedure, because we already have a lot of tools in our deep learning toolkit, and we don't want to be reinventing the wheel and having to recreate every one of the techniques that's already out there. So let's do this with a concrete example that may make it a little easier to think about. So we're going to do multi-class classification. This is a problem that everyone's seen before. We have some deep network, and we have 3 classes. And now we have an output for each class that's going to predict the probability of that class. And what we'd like to say is that we're doing multi-class classification, so we want exactly one class to be predicted. We can express this pretty easily in propositional logic. And now we're a little bit stuck, right? We're working with logic, so maybe we want to round every probability and get Boolean values. We can see that the constraint is not satisfied, but we're not learning anything, and we don't really have any information to feed to our network to update. So why is this so difficult? Like, why are these two things so hard to mix? Deep learning and logic are both currently like fundamental parts of AI. We don't really want to be doing this context switch every single time we need to use both. And it kind of fundamentally, it's because they live in different spaces, right? Deep learning works with these functions that are continuous, they're smooth, they're differentiable. They're the kinds of functions you might see in like a calculus class or something. Whereas logic tends to deal with discrete objects. We do a lot of symbolic manipulation, and it also has this like very strong semantics. Things in logic have like a very concrete meaning, which is not an obstacle that we have to deal with in deep learning. So our approach is we're going to bridge these two by using a probabilistic interpretation of the logic. And what do I mean by that? Well, we can take the outputs of this neural network. We just have a probability for each label. And we can say we're going to treat each of these as an independent Bernoulli random variable. And now we can say, well, why don't we just compute the probability that the constraint is satisfied and optimize that instead? So in this case, we can write down the formula pretty easily. You can just read it straight from the logic. And we can see, in this particular case, maybe there's a 19% chance that it's satisfied, so this is not great. We might want to increase it. But this function for a particular constraint is what we call semantic loss. And it's basically our way of bridging this gap. So semantic loss is a smooth, continuous, and easily differentiable function. So it'll fit into your deep learning framework. But it represents how close your outputs are to satisfying the constraint. And moreover, it's axiomatically, like by construction, respects the semantics of logic, and it maintains the precise meaning. This is not a syntactic approximation. It doesn't matter how you write out your logic. As long as it has the same meaning, as long as it has the same truth table, the function is going to be exactly the same. Okay, so this is nice. But as I mentioned, we sometimes have to do some difficult manipulation with logic. How do we compute this semantic loss? And furthermore, actually, how do we compute the derivatives? Because we're doing deep learning, we're going to need those to do backpropagation. So it turns out that in general, this problem is Sharpie hard, which is not that surprising since we're dealing with logic. But borrowing from the techniques of knowledge compilation, of logical circuits, we actually know that for a lot of logic, even pretty difficult things, we can compile a circuit that's fairly compact. And once we have that circuit, we can do all of these operations in linear time. So we can compute the probability, we can compute all these derivatives, all pretty easily in linear time. Okay, so let's look at some empirical evaluations. We want to make sure that this is doing, kind of what we think it's doing. So first we start with supervised learning. So we're going to say you have a grid. We're going to randomly remove a bunch of edges, and then we're going to pick 2 nodes, and we're going to try and have the network predict the shortest path between them. And it's going to do that by basically giving us a binary output for every edge, telling us whether or not it's included in the shortest path. We are going to build a simple MLP to predict this, and then we're also going to do it separately with semantic loss, where we have a function representing the constraint that we only want it to be predicting paths, right? If you have a shortest path algorithm and your algorithm predicts a bunch of disconnected edges, it doesn't really make any sense. So we do this, and then we have our comparison. So we find that the MLP can only even predict a valid path about 7% of the time, despite the fact that every piece of training data has a valid path, because the training data is all shortest paths, and we can bump that up to about 70%. The number of true edges being predicted, like if you don't look by the structure, is the same, which tells us we're not adding any expressive power at all to the network. There are no parameters being added. And finally, the actual accuracy is increasing immensely, right? We're going from maybe 6% to about 29% accuracy. So it's doing pretty much what we want it to be doing. And the next area where we tried to use this was maybe a more familiar problem that was discussed earlier, which is semi-supervised learning. And the intuition here is that, unlabeled data has to have some label from your data set. So we want to make our classifier try to actually predict something. So on unlabeled data, we provide it with the exactly one constraint that I talked about earlier, try to force it to make a prediction. And we did, there's more comparisons in the paper. This is in particular just fashion. We found that we were doing pretty well, even in comparison to sort of highly tuned specific to semi-supervised learning methods, despite the fact that we're basically just adding a special case of one loss term. Okay, so to conclude, if you take away one thing from this talk, I want it to be that you can combine deep learning and logic using a probabilistic semantics. It's not this impenetrable wall. And you can do this all while maintaining the precise meaning of the logic, and while also fitting right into the deep learning framework and thus getting the best of both worlds. Okay, come check out our poster. There's more results if you want that. There's more math if you want that too. And we have code online that's pretty straightforward to use. Thanks.
So while the next speaker can prepare itself, we have time for 1 or 2 questions. All right, I have one. What is the train and test time for your method?
That depends a lot on what type of constraint you're using. For that exactly one constraint I described, it's exactly the same as the network. If you make your constraint very complicated, then obviously it'll grow and surpass it. In our examples, we didn't have anything that increased it by more than 50%. But conceivably, if you make an arbitrarily large logic, then yeah, you can make it take as long.
And is there a way of approximating that?
That's kind of future work.
Oh, there is one question there.
I was just going to ask about future work. Are you planning to extend on this and how?
Yeah, so I think, like was mentioned, I think approximating it is, at some point, depending on what type of usage, it will be important. I think another interesting direction could be first order logic, because it may be kind of easier to apply directly. Yeah, I think that those are pretty interesting directions.
All right, let's thank the speaker again. Right. So the next talk is by Aditya Gilra, and it's about nonlinear motor control by local learning in spiking neural networks.
Hi, everyone. I'm going to talk about learning nonlinear motor control as the brain might in spiking neural networks and locally. This was work done as a postdoc at the EPFL, and now I'm a postdoc at the University of Bonn. So animals and humans are pretty good at motor control. We all know this, but we are not born this way. We need to learn from infanthood. And one of the ways the brain might learn this is thought to be by learning internal models of how our muscles and body move in response to neural commands. So for concreteness, we look at an arm modeled as a two-link pendulum. The brain would send motor commands, neural activations of muscles, which we will just represent as torques, two torques to the two joints of the two-link pendulum. And at the same time, the brain receives feedback, both visual and proprioceptive, to compute the arm state, the state of the arm. And of course, the arm has some nonlinear dynamics. The state evolves dx by dt as some function of the current state and the input. So the internal models that we are going to learn here will be one, the forward model, which is given the input torque. The brain must predict what is the state of the arm. And the inverse model, given the desired state of the arm, the desired arm trajectory, what is the torque that would generate this trajectory, this arm state trajectory? And one can use, the brain could use the forward model, for example, for planning. So given the torque as a function of time, what would be the state? And the inverse model for control. So for example, in feed-forward control, the inverse model, you just feed in the desired trajectory of the arm, and the inverse model should give you the torques that should be given to the arm. So, I mean, here we are looking at learning these models as the brain might learn them, and the brain has various constraints. For example, the brain uses spiking neurons. So unlike artificial neurons, which have usually continuous values at every time step, the brain just generates events or spikes which are transmitted at sparse time steps. So if there's neuron J communicating to neuron I, the signal that goes is an all or none signal at very specific, at some time, asynchronous time points. However, this signal here, this spike, is transmitted to the next neuron I, where it transduces a current into this membrane, which acts like a capacitor. And this current is just a low-pass filter of this spike train represented as the sum of delta functions. So if you filter it with this kernel kappa, which is a decaying exponential, typical time constant is around 20 milliseconds, then you get the current. And then further, the capacitive membrane acts again to low-pass filter this current to get you a voltage in the neuron. And every time the voltage of the neuron crosses a threshold, it spikes again. And this is again propagated to further neurons. So this is how the brain uses spiking neurons, and this is what we will use. Of course, as a proxy for the continuous value, you can choose the activation into the current in the next neuron as a proxy for a continuous value that is getting passed. But for long distances, it's the binary value, that binary spikes that get passed. A more important constraint is that the brain can only change its weights locally. So the weight Wij between two neurons can only be affected by quantities that are available locally in space and in time. So for example, local quantities could be the presynaptic firing rate or some current in the postsynaptic neuron and so on. And actually, this is not just useful for figuring out how the brain might do it, but also in neuromorphic computing. The brain is very efficient, and there are many people now making integrated circuits that use spiking neurons for energy-efficient transmission between neurons. And local rules would ease hardware implementation and allow distributed learning. So you don't need one central computer for weight changes. So what is the difficulty in finding these local learning rules? So now if you were to just do a nonlinear kinematic transform, so given you just some nonlinear transformation to X, you would use a simple one hidden layer multi-perceptron, and you can, so if you are given fixed and random encoding weights E, then from the function approximation theorem, you know that you can always find some set of decoders that will approximate G arbitrarily closely as long as you have a large number of heterogeneous neurons here in the middle layer. However, what we want for the forward model is a nonlinear dynamic transform, where you have to integrate U to get X. So for this, you require a recurrent neural network. This is where this low-pass filtering or leaky integration of these neurons helps, because the W effectively implements the function F, and the integration of X is done because of the integrating nature of these neurons. But now with a recurrent network, even with fixed random input weights E, you require backpropagation through time to learn Ws and Ds. And backpropagation through time is, of course, non-local in time, so this will not work. So we are looking at finding a local learning rules, and earlier we came up with this follow learning rule, feedback-based online local learning of weights. The basic ideas of this are borrowed from adaptive control theory, and these are further references. And I will soon explain what this is. So we are going to learn the forward and inverse model of the two-link arm for concreteness using our follow learning scheme. So once again, the motor command U, a two-dimensional torque, is sent to the two-link pendulum or the arm, and from visual and proprioceptive feedback, we obtain the reference state X. And now the same motor command goes to some brain area which is acting as a forward model, and this predicts some state X hat. X hat is compared to the reference X and an error generated, and this error will be fed back as an extra input into this model and will serve to modify the weights here. And this, of course, this is a supervised learning scheme. You require the error at every time point, but for a human body or an animal body, this is easily available. It's self-supervised because as an infant, just like vocal babbling, infants randomly move their arms around. So basically, random motor commands are being generated, and the arm moves in a random way, and from these observations, the brain can construct this model by just motor babbling. So this is labeled data is not a problem here for motor control, at least, for learning the inverse and forward models. So similarly, apart from the forward model, the brain can learn the inverse model. So instead of the motor command, now the input is the true state. And here, given the true state trajectory as a function of time, the inferred command has to be learned. You have to infer the command that generated this trajectory. Of course, you can only, due to causality, you can only infer the previous command that generated this, so you require a delay here. So you have to compare the inferred command to the slightly earlier command. And again, this error is going to be fed back. So now, since we are in the neural network architecture track, we have two architectures to propose here. One is the architecture of follow learning, which I will explain, the way this error is fed back and the way local learning can proceed. And the second is the architecture of the forward and the inverse model itself. We will see that we really require two different kinds of architectures for learning the forward and inverse model. So two architectures. First, the follow architecture for learning. So we just initially consider the forward model. The motor command is fed with fixed random input weights. The weights in red are going to be learned, in black are fixed. And the current in one of these neurons, I, the total input, is the sum of the feed-forward input and the recurrent input, and with some biases. These are, again, random, but different. So that basically then you can use function approximation using these heterogeneous neurons to decode the readout, to decode X hat, the predicted state, linearly with these weights D. So now in the motor babbling paradigm, if a random input U is given as a torque, then we would like to generate the reference in blue, but initially, of course, without learning, the network just generates the red prediction. And now we are going to feed the error back, but for feeding it back, there is a special scheme. Again, this is the trick from adaptive control theory, that the error is going to be fed back with fixed random error feedback weights EI alpha, but the output weights D alpha I are going to be learned, pre-learned. So we will set these readout weights to form an autoencoder with the error feedback weights with gain K, such that if I feed in epsilon alpha here, which is multidimensional, the output in the open loop case is K epsilon alpha. So this is the trick from adaptive control theory. And this we assume to be pre-learned, and here we just set them algorithmically, but there are other people who show how this can be learned by a local learning rule, because this is just simple learning of the output weights with a perceptronal rule. So now let's close the loop again. So this is the dynamical system or the ARM. The motor command goes there. We get the reference state from visual feedback or proprioceptive feedback. The network is predicting x hat. These are compared, and the error is fed back as a third input. Now note that we learned these weights d alpha I such that if I feed in epsilon here, the output x hat is k times epsilon, and epsilon is just x minus x hat. So solving this consistently, we get x hat is approximately x, if k is large. So this is just negative feedback from adaptive control. So what happens is, even without learning, the predicted state x hat is following the reference state x. So this is the trick from adaptive control. And now, given the input u, we see that the red prediction follows the blue reference. Of course, there's no learning yet. If we cut off the loop, it's going to go back to not following. And what's interesting is not just this low-dimensional, four-dimensional variable following it, but actually because the error is driving these neurons, each of these neurons is already, its activity is close to the ideal activity that it should have to generate x. And this will enable, this is the trick to enable us to have local learning. The activities here are already ideal right from the start, even without learning on the weights. So now we come to the learning rule. The current in one of these neurons is the sum of the feed-forward input, the recurrent input, and now this extra current, which is the error current. And this error current can now be used in local Hebbian-like rule or perceptron rule, for example. This is the postsynaptic error current, which is being fed in here, times the presynaptic activity. And the presynaptic activity is already close to ideal, so the error directly can change the weights. So it's a simple perceptron rule, and this can be derived from a Lyapunov stability principle, ensuring that the learning is stable. And this is the trick from adaptive control. So now we use this learning rule to follow, to learn a two-link ARM forward model. So as I already mentioned, with feedback off, given input u, the network in red does not follow the output, the reference. But then the moment you turn on feedback, it starts to follow, but there is a small error, and this error drives learning, so that at the end of learning, when you remove the feedback, then the prediction is the same as the reference. So now without feedback, the ARM is doing what it should. And now, so if you were to give some torques to the reference ARM to make it reach the sine square, and you give the same to the network repeats. So this is with feedback cut off. So even then it follows exactly what the reference is supposed to do, as in it predicts what the reference. Similarly, you can have an acrobat-like task where only small torques are given at the elbow joint, like at the hip joint, and you can reach the sine square only by swinging and not directly. And there also, the reference is in blue and the predictive model is in red. Again, the feedback is cut off, and just it's integrating the torque to give the state. So this was learning the forward model. Similarly, we can learn the inverse model via follow. And here, of course, as I mentioned before, it is the true state of the ARM that is fed as the input during learning. And then the network has to infer the control torque that produced the ARM state. And of course, due to causality, you can only learn it with a delay. And here, as I mentioned, the feed-forward plus recurrent network doesn't really work. What you need is what we term a differential feed-forward network. In fact, if you try to put in some recurrence here, the learning goes haywire and the error starts to increase. So what you require is the direct state to one part of the first layer and a delayed state to a second part of the first layer, and then these are fed in with plastic weights in red to a third layer, which then gives the output. And why do we require this different network compared to the forward model? Because in the forward model, you have to integrate u to get x, which is why you require that recurrent network, because you have these leaky integrators which integrate the input. And whereas if you make it recurrent here, this won't work, because what you need for the inverse is to differentiate x and then invert f to get u. So that's why you require two very different architectures with spiking neurons, with the biological neurons, and so on. And of course, to make it local. Of course, you can learn it with backprop through time, with LSTMs and so on, but then it would not be local, not biologically plausible, not with leaky integrating neurons. The parameters can be varied. Typically, you require this delay to be of the order of the time it takes for, the two synaptic delays, 20 milliseconds each. So now you can use this inverse model after it has been learned. The weights are fixed. And if you feed in the desired state here to the input, the inverse model tells you the control torque that should be given to the arm so that the arm essentially follows what the desired state that you want. Of course, there will be a small error due to approximation, and that error can be corrected by simple proportional linear feedback. So this one does the nonlinear control, and then around it you can do a small linear proportional control. And this, of course, we then, in open loop is like drawing this trajectory with eyes closed, and closed loop is, let's say, with eyes open, so with feedback and without feedback. And in summary, we proposed a follow scheme, an architecture to learn, which is based on adaptive control theory, for learning nonlinear dynamics in spiking neurons as the brain might via stable, online, and local plasticity. And the stability proof, we have a proof similar to adaptive control based on Lyapunov function, and you can see it in the paper and the poster. And apart from this architecture for local learning, we also showed that for forward versus inverse model, the architectures are very different, recurrent versus differential feed-forward. We then use the inverse model for motor control. Further, we would like to put in further biological constraints and compare with experiments. Also, as I mentioned, there are applications to neuromorphic computing for power efficiency and easy learning rules. We are looking at hierarchical networks because in the brain also there are hierarchies of motor control: spinal cord, brainstem, cerebellum, motor cortex, premotor cortex. And finally, currently we were giving the full desired trajectory, and then the inverse model was producing the torque. But let's say only the endpoint is given, or only a higher order goal is given, then you would require reinforcement learning. So we are looking how to combine these forward inverse models with reinforcement learning or other reward-based learning for motor control. And thanks to the old lab where this work was done with Wolfram, and my current lab and my funding sources, thank you for your attention, and the code is available, and there's the poster number 2 tonight. Thank you.
All right, we have a few minutes for questions. Meanwhile, the next speaker can come to the podium. So I have a question. So did you try more fancy feedback to reduce the oscillations and offset during training?
We didn't. So typically in the brain there is not very strong feedback. So we were using proportional feedback k equal to 3. But one could try, for example, integral and differential feedback also. But here it's more proof of principle, so we did not go too much into performance. It's more architecture and ensuring we get a local learning rule which works.
Just to let you know, the microphone are over there if you want to ask question. I have another question, which is that you have an approximation that causes errors in your and that should cause like some weight drifts. Do you see that happening during your training, or what?
If we use a large enough number of neurons in the middle layers, we approximate well, and then we don't. But in adaptive control, again, there are tricks to control this drift of weights in that literature. But we didn't need to use it. As long as we used around 2,000 neurons in the middle layers, it worked fine for this kind of an example.
But with smaller number of neurons, you will need that?
Yes, you would need some control on, due to approximation error, there will be drift of weights, and we will have to use various techniques from adaptive control to again control that.
All right, let's thank the speaker again. So the next talk is by Yunbo Wang, and it is called PredRNN++ towards a resolution of the deep in time dilemma in spatiotemporal predictive learning.
Okay, hello everyone. My name is Yunbo Wang, and I'm a third-year PhD student from Tsinghua University. I'm co-supervised by Professor Longming Sheng and Philip Yu. And I'm very happy to introduce our work here. Our model is called PredRNN++, which is named after our previous version published on the NIPS conference last year. And at this time, we try to solve the deep in time dilemma in spatial temporal predictive learning. Okay, here is the formulation of spatial temporal predictive learning. Basically, it is a type of sequential data. And I think the values of predictive learning has two aspects. The first one is that we can use the predictive learning to do the video frame prediction. For example, the weather forecasting based on the consecutive radar maps. And the second one is that we can use the spatial temporal predictive learning to as a self-supervised or unsupervised feature learning method to assist the other tasks such as video classification or video captioning or extra. One category of the previous architectures are mostly based on the RNNs, and sequence-to-sequence LSTMs are used to model the temporal dependencies. And researchers also inject the convolutions into the LSTM cells, including the input-to-state and state-to-state recurrent transitions. And our model is basically a RN model. Another category of previous architectures are based on the CNNs. They always use the adversarial training, combined adversarial training with the CNNs. And recently, more complex models have been proposed, including the DeepMind model, VPN, and our model, pre-RN. Here's our motivation. The pre-RN model, the previous version, uses a zigzag memory flow. The good thing is that the zigzag memory flow provides more straightforward supervisions to the training of the memory structures. And also, it adds more recurrent computing unit in local temporal neighborhoods so that the model can capture the short-term dependencies, especially the sudden changes in the videos quite well. But these models, these deeper in time models, suffers from gradient vanishing, so that they suffers from bad long-term modeling capability. Our insight is that both the short-term and the long-term relations are very important in video prediction or spatial temporal predictive learning. And the first contribution of our model is the causal LSTM. We call it causal LSTM because it has a dual memory structure. The first memory cell is the conventional LSTM memory, and we set it on the base of our LSTM unit. And another memory cell is newly proposed. We call it spatial temporal memory, denoted by the MTK here. And it has a zigzag memory flow. And we connect these two memory cells in a cascaded structure so that we can make our model deeper in the, from one time step to the next one. And in this way, we add more nonlinear layers in the local temporal neighborhood. Yeah. And here is the key equations of our LSTM unit. And the second contribution is we propose the gradient highway unit, which provides a shorter path for the long-term relations. And it basically it functions like a switch, enabling an adaptive learning between the quickly updated representations produced by causal LSTMs and lazily updated representations produced by this unit. And in this way, it can capture the long-term dependencies and keeps the gradients from vanishing. And we test our model on two video prediction data sets. The first one is the moving MNIST. We found that the moving MNIST data set are quite challenging because there are frequent occlusions in this data set. As you can see, 2 digits are flying in the video, and they overlaps from time to time, both in the input sequence and the target output sequence. And the third line are the results of our model, and lower lines are the compared models. Yeah, and as you can see, our model can maintain the shape of the 2 digits, especially the digit 8 in the first example. And the compared models, including the most powerful one, VPN, cannot maintain the shape of this digit. And we counted the frequency of the occlusions in this data set, as you can see in the bar chart, and it has a bowl shape, a reversed bowl shape. And we also print the gradient curve back in time of our model, as you can see in the as the blue line, the blue curve, and it has a corresponding bowl shape. Yeah. And we evaluate our model on another dataset called KTH. And this dataset, in this dataset, there are periodical human movements. And our model can predict the trajectory of the movement and also maintains the figure of the people. And we have a prototype system and help the Chinese government to do weather forecasting. And here is an example of a severe weather condition happened earlier this year. Yeah, it's in the Jiangxi province, China. And because of the strong wind, the roof, the ceiling of the airport collapsed. Yeah. And afterwards, the government tested our model and used the data that day, and they found that our model achieved better results, better prediction results than their older systems. So if we use it earlier, maybe we can do something, we can take the precaution. Okay, thanks for listening, and looking forward to seeing you at the poster session tonight. Thank you.
So there is time for a few questions. The microphone are on each side.
Hi. So is there any notion of uncertainty in your model in the latent space? In other words, like if I'm observing the weather.
Yeah, I know what you mean. Some work use the variational autoencoder or something else to model the uncertainty of the future. Yeah, but in our work, we just want to focus on the deep learning architecture.
I see. So this is like moving MNIST where there's like certainty where it's going. Yeah. In other words, and that, those kinds of models where. Okay. Thank you.
If there is no other question, let's thank the speaker again.
Thank you.
All right. The next talk is by Nivan Wishers, and it is called Hierarchical Long-Term Video Prediction Without Supervision.
Hello. So yeah, I'm Nivan. I'll be talking about our video prediction model. So the task of video prediction is given the first few frames of a video's context to predict the next frames in that video. So that could be useful for a couple of different reasons. One of them is unsupervised feature learning, where the features that we learn for video prediction can be useful for other tasks, such as human pose prediction. Another potential application is in reinforcement learning, where it would help an agent to have an accurate model of the world, and such a model could be learned through video prediction. There's a number of related works on this topic, but most of them fail to do long-term prediction far into the future. An example of a related work is the method by Chelsea Finn et al. That works by explicitly predicting the motion from one frame to the next. An example of a method that does do well on long-term video prediction is the previous work of Rubin Villages et al. And this method works by first encoding each of the input frames to get the human pose, the pose of the person in those frames, and then predicting what the pose will be in future frames. And then those pose predictions are decoded to get what the actual frames are going to be. The disadvantage of this method, though, is that it requires supervision in the form of having to have all of these human poses annotated in order to train each of the networks shown here. So for our work, we look at how we can take such a hierarchical long-term video prediction method and then train this without supervision. So in order to do this, at inference time, we take our first image and then encode it with an encoder network to produce a one-dimensional representation of this image. Then we predict what that encoding will be at the future time step using an LSTM. And finally, that prediction is decoded to get the prediction of the image frame. Notice that here our decoder takes in the first frame and the first encoding, so then the predictor network here doesn't have to represent information that is already contained in the first frame. So for the number of context frames that we have, this procedure is similar, where again the decoder is given the first image and first encoding, and the hidden state of the LSTM is passed through into the next time step. And at some point after there aren't any more context frames, instead of feeding in the output from the encoder on the image, we have to feed in the previous prediction of the LSTM network into the next state of the LSTM. So notice that here the network can learn its own encoding space to do these video predictions in. And also note that the predictions of the decoder are never fed back into the network, so errors that the decoder makes are not propagated onward. There are several methods that we can use for training this. One very simple method is to optimize the end-to-end loss on the frames that are predicted compared to the ground truth frames. However, this produces very blurry results because the decoder is going to output something blurry if the predictor network here is uncertain. To overcome this problem, it helps to split up the training of the decoder and predictor network. So here I show how the encoder and decoder can be trained at the same time, similar to how an autoencoder works. So in this method, the image is given to the encoder and then decoded again by the decoder, and we're just optimizing the L2 loss here. So this encourages the decoder to produce sharper predictions because here there isn't any uncertainty because it has indirect access to the ground truth image through the encoder. And then also the encoder, of course, will learn to produce encodings that can be decoded to recover the image. So by the way, the architecture of our decoder here is a visual analogy network, and as part of that, we take the encoding that's fed in here and then subtract the first encoding from it, so that way the network has a very clear signal of what has changed from the first encoding here. So also in this method, we train the encoder and predictor together, so that way we want the predictor network to be able to predict the next encoding in the sequence. So we just minimize the L2 loss between that predictor network and the encoder network. And again, here the encoder network is also trained, so that way the encoder can produce encodings that are easy to predict into the future. So this one shows the full method that I just described, where the encoder has to make a trade-off between making encodings that are informative enough to generate the image and also encodings that are easy to predict into the future. So in this way, the network learns what higher level space to put these encodings in order to make future predictions easy. One disadvantage of this training procedure, however, is that the L2 loss is still optimized between the LSTM network and the encoder. So it can produce blurry predictions in this encoding space that the decoder doesn't know how to decode. So to alleviate this problem, we can train this with an adversarial loss where all of the outputs from the predictor and also all the outputs from the encoder are fed into a discriminator network. And that discriminator tries to tell the difference between the two, while the encoder and predictor are both optimized to fool the discriminator. So this helps both because in this way the LSTM network will be encouraged to make high quality predictions so that can fool the discriminator, and those will probably be ones that the encoder can be able to decode easily. And also, the LSTM network will be motivated to make predictions that change over time, or else the discriminator network will know that they are not valid ones. So to present our results, we experiment on the data set shown here. There's a shapes data set that we created with simple objects moving around, and also the popular Humans 3.6M data set. For baselines, we used the one from Chelsea Finn presented earlier, and then also method from Denton and Fergus also presented in this conference. So on our shapes data set, we find that the predictions from ours here can produce some clear predictions up until about 1,000 frames into the future, where the method from Finn et al. Disappears or gets blurry over time. To measure this quantitatively, we create some simple heuristics to measure if the shape with the correct color is present in our last frame. We find that in ours that happens about 97% of the time, where in the baseline it happens about 25% of the time. On the Humans 3.6M data set, we find that ours can produce sharp predictions for our adversarial method about 20 seconds into the future, while the baseline methods usually disappear or blur out over time. To further validate this, we send the videos to raters and ask them to do a side-by-side comparison of it. And we find that versus Finn et al., they rate ours as better about 74% of the time, and versus Denton and Fergus, rating ours as better about 58% of the time, versus theirs is better about 18% of the time. To further validate this, we run a pre-trained person detector over the frames generated from our video versus our baselines, and we find that the person detector is consistently more confident that there is a person present in frames from our videos versus frames from the baseline videos. To validate that the features learned by our network are useful for other tasks, we take the features learned by our method and then train a simple network to estimate human pose based on that, and then also train the same network to calculate the human pose just based on the features from a VGGNet trained for recognition. And we find that when trained on ours, it gets a 9% improvement relative to the one trained for recognition. So in conclusion, this architecture and long-term training strategy can produce sharp predictions up until about 20 seconds into the future, and the network can automatically discover this higher level space that's useful for video prediction and also other tasks like the pose prediction. So for future work, it might make sense to try other methods in this higher level space, for example, the previous work by Mohammed. And thanks for your time, and I think that there's time for questions now, and also you can come to my poster at number 131. And on GitHub, we have the code for this method, and you can scan this for the paper and more.
All right, we have time for a couple of questions.
Okay, so nice presentation. So in your motivation, you talked about reinforcement learning as one of the applications.
Yeah.
So one difficulty in RL is your models are really action conditional, depends on your policy. In the case of multi-step models, they're really policy conditional. So I wanted to see what your insights are when you have to incorporate policy too in your model. How would you do it?
Yes, so as far as the action conditioned, we did do some experiments on other data sets where the action was fed into the predictor network, and we found that we can incorporate those easily. So the only change would be for our predictor network, instead of just feeding in the encoding, we would feed in the encoding and also the action.
Okay, and do you have any thoughts if how you would provide the policy? Like, multiple actions, or like a network that produces actions?
Haven't looked into that area too much,
Okay.
but it might be an interesting one for future work.
Okay, thank you.
Okay, thanks the speaker again. Let's move on to the next talk. So the next speaker is Masanori Suganuma, and he's going to talk about exploiting the potential of standard convolutional autoencoders for image resolution by evolutionary search.
Thank you for introduction. My name is Masanori Suganuma. I'm from Riken Center for IP and Tohoku University. Today, I will talk about image illustration using evolutionary search. Image illustration is to recover a clean image from its corrupted version, like this figure. So in order to solve this task, learning-based methods which use CNNs have been introduced recently and have shown good performance. In these studies, researchers have approached the problem mainly from two directions. First one is to design new network architectures. For example, the network of the bottom left is called MemNet, which contains a lot of recursive connections and a lot of gate units. The other is to develop new loss functions or training methods. A recent trend is to use adversarial training, in which a generator is trained to perform image restoration, and a discriminator is trained to distinguish whether an input image is true image or recovered one by the generator. So many good approaches have been proposed so far, but I want to ask a question. Are standard network architectures optimized enough? In other words, have we fully explored the space of standard architectures? We believe that there is still much room for exploration of such spaces of standard architectures. For example, the depth of a network, the number and size of filters in each layer, and adding skip connections or not. So in this work, we show that standard convolutional autoencoders can outperform existing methods when they have appropriate architectures. Then, how can we design architectures? Recently, many architecture search methods have been proposed. The recent studies are roughly divided into three categories: those based on evolutionary approach, reinforcement learning approach, and other techniques. In this work, we employ the evolutionary approach previously proposed by us due to its computational efficiency. But we think other very recent lightweight methods can also be employed for this purpose. Next, we will introduce our method. In our method, we represent CAE architectures by directed acyclic graphs, where each node represents a convolution layer followed by ReLU, and each edge represents a connectivity of two layers. The graph is called phenotype and is encoded by genotype in this work. A genotype consists of integers, and each integer represents the attributes of a layer, such as the number and size of filters and connections of each layer. And this figure shows an example of genotype, a phenotype, and corresponding CAE architecture. The input of each node in the phenotype is connected to the at most one node. So there is a single unique path starting from the input node and ending at the output node. This path represents the encoder part of the CAE. We employ a symmetric CAE in this work, so the decoder part is designed to be symmetric to the encoder part. So we optimize a genotype to maximize the performance by evolutionary computation. Specifically, we optimize the number and size of filters and skip connections of each layer in this work. So we will move on to the experiment. In this work, we test our method on inpainting and denoising tasks. We basically follow the same experimental settings as previous studies. For inpainting, we prepare 3 mask patterns: center mask, pixel mask, and half mask. And we use 3 benchmark datasets: Survey dataset, CARS dataset, and SVHN dataset. And for denoising, we prepare Gaussian noise with 3 noise levels, and we use a PSD dataset. So this is the result of the inpainting task. Each column shows the result of each method, and each row shows the mask pattern. So as you can see from these images, our method performs well and generates realistic images compared to the state-of-the-art method. And this table shows the PSNR and SSIM values on test images. Our method outperforms the other 2 methods for all dataset and mask combinations. So this is the result of the denoising task. As you can see from this figure, our method performs well. And this table shows the PSNR and SSIM results. And our method outperforms the state-of-the-art methods. In addition, RedNet has 30 layers and MemNet has 80 layers, but our best architecture has only 15 layers. So we can conclude from these results, our method was able to find simpler architectures that can provide more accurate results. These are examples of the architectures designed by our method. The top one is for inpainting networks. Sorry, top one is for inpainting task, and the bottom one is for denoising task. As you can see from this figure, the number and size of filters are different across layers, which are difficult to manually determine. Although it is very difficult to give a general interpretation of why the parameters of each layer selected, but we can make some observations. The first one is almost all networks have skip connections at the first layer. This implies that input images contain essential information to generate accurate outputs. Next, when comparing optimized inpainting networks with optimized denoising networks, 5x5 filters tend to be employed in the inpainting networks more often than denoising networks. In contrast, 1x1 filters tend to be used in the networks for denoising more often than inpainting networks. So finally, let me summarize this work. We have observed that simple CAE can provide good performance when they have appropriate architectures. Therefore, it is very important to carefully design the architecture of your network. But it is also observed that our method tends to yield less sharp outputs for input images with large missing pixels, such as half-mask patterns. Bottom one. So we think this is due to the employment of the L2 function. In this work, we use just L2 function for optimization. Of course, we recognize that not only architectures but also loss functions or training strategies do affect our performance a lot. For example, adversarial training can provide sharp images. So in the future, we think performance can be further improved by combining good architectures and adversarial training or other sophisticated loss functions. So this is all from our presentation. Thank you.
We have time for a few questions. So I have one. How do you initialize your architecture?
Okay, in this work, we initialize our architecture at random.
Yeah. And have you tried to initialize it with an architecture that is known to be very good, just to see if you diverge from it or if it's a local minimum of architecture?
No, I haven't. So next, I will try that.
There's one question here.
Hi, it wasn't clear to me the fitness function that you used for the evolutionary part. When you say performance, do you mean like training it for a certain amount of epochs?
Yes. So in this work, we use the PSNS value as a fitness function. And so in this case, to maximize the fitness value, to maximize the PSNR value on the validation dataset, we optimize the genotype by using evolutionary computation.
All right, let's thank the speaker again. Okay, the last speaker of the day is Tao Qin, and he's going to present a paper called Model Level Dual Learning.
Okay, thanks, Chair, for the nice introduction. So this is Tao Qin from Microsoft Research Asia. I will present our work, Model Level Dual Learning. So this is joint work with my intern Yingce Xia, my colleagues Yitan, Fei Tian, Tian Liu, and Professor Nenhai Yu. So what's dual learning? So we know that symmetry in our world is very common. Both nature and our human favor symmetry. We think that things that are symmetric are beautiful, including, for example, butterfly, our human face, and also Taj Mahal or yin-yang fish. Actually, symmetry is also very common in artificial intelligence. We see that two tasks are symmetric if one task mapping from space X to space Y, and the other task maps from space Y to space X. For example, in machine translation, the translation from English to Chinese and the translation from Chinese to English are symmetric. In speech processing, the task of speech recognition and the task of speech synthesis are symmetric. In image understanding, the task of image captioning and the task of image generation condition on a given text sequence are symmetric. And also in conversation, the task of question answering and the task of question generation are symmetric. And also in search engine, the task of search, that is matching web pages for a given query, and the task of keyword suggestion, and that means matching keywords for a given advertisement, they are symmetric. So we call the task of from space X to space Y the primary task, and the task of from space Y to X the dual task. So dual learning is a learning framework that leverages the symmetry or primary dual structure of AI tasks to boost machine learning algorithms. Dual learning has been studied from different settings, such as unsupervised setting, supervised setting, inference, or transfer setting. Actually, all of them focus on data level duality. For example, in unsupervised setting, it focuses on the translation or the mapping from X to Y and then back to X, and aims at minimizing the reconstruction error. In supervised setting, it tries to achieve the consistency between the joint probability computed by the primary model or the dual model. In this work, we take a further step. We consider the model level duality, because duality exists not only in data level, but also in model level. Let's take machine translation example. Suppose the primary task is translation from X language to Y language. Usually, for neural network-based methods, we have encoder. It will take the X sentence as input and output a set of hidden representations. And we have another decoder works on Y language. It will take the hidden states from the encoder as inputs and decode and generate a set or a sequence of Y words. Similarly, for the dual task, it has an encoder working on the Y language and has a decoder to generate X language. It's easy to observe that the encoder in the primary model and the decoder in the dual model, they are very similar. They share very similar model architecture. For example, both are RN, or both are CNN or self-attention. And they both work on X language. Similarly, the decoder in the primary model and the encoder in the dual model, they both work on the Y language, and they share very similar architecture. Therefore, we propose to share the model or share the model components. For example, we can share the encoder in the primary model and the decoder in the dual model, and share the decoder in the primary model and the encoder in the dual model. Doing so, we can couple the two models together, and we can jointly train them together so that we can enhance the knowledge transfer or regularize each other during training. Okay. So let's have a look at technical details. So we first check the symmetric setting. For symmetric setting, here we consider a specific task we call sequence-to-sequence learning. Both X space and Y space are sequence, but maybe one may be the, for example, Chinese, and another may be English. Okay. So here we decompose the encoder-decoder into two components, the X component and the Y component. X component will focus on X language, and the Y component will focus on Y language. So here, one component can serve as both encoder or decoder, depends whether it's used the input or output. So here you can see that the X component will take X as the original input, and the CX, we call it information set as input, and generate a set of hidden state HX. Y component similarly will take Y and CY as input, and generate a set of hidden states HY. So these two components can compose both the prime model and the dual model, but in different orders. So let's have a look at the primary model. So you can see here, the X component will be used as an encoder. Because for encoder, we only have the original sequence X as input. So here, the CX and the ZX will be 0, they are empty set. And it will generate a set of hidden states HX. For Y component, it will serve as decoder. So it will take both the already generated Y previous words and the hidden states from the encoder as input. So here, CY will be equivalent to HX. Okay. So you can see this, this figure shows the architecture of the primary model. Similarly, we can use the two components to compose the dual model, but in different order. So here, Y, because the dual model is a translation from Y language to X language. So Y component will serve the encoder. Here, you can see the CY and ZY will be empty or 0. And the X component will serve as a decoder, so it will take the hidden states generated from Y as input, and also the previous generated words X as input. This is for dual model. So you can see that the prime model and dual model, they share the same components, but in different order, so that we can achieve the model compactness. We can experiment on different machine translation data sets. Here is the results on a small data set, German to German English translation. The training data scale is about 100K bilingual sentence pairs. We compare with traditional methods and GKRU, RN-based, and also CNN-based plus IL, and most recent work, Transformer. So our method is also based on Transformer, but apply our model level duality, model level sharing. So you can see we can improve the accuracy in terms of BLEU score for about 1 or 2 points for both directions. We also conduct experiments on Chinese English translation. This data scale is relatively middle scale, so we have about 1.2 million bilingual sentence pairs. We also achieve improvements on both directions. Here is the results. Relative large data sets with about 4.5 million bilingual sentence pairs. We achieved improvements about half BLEU points for both directions. Okay. We also applied our idea to asymmetrical setting. In asymmetrical setting, it's more like classification. The input is like a text sequence, but the output is a category or category labels. So you can say X space somehow is more complex than Y space. Okay. So here the primary task is text classification. The dual task is like text generation. For example, given I want you to generate a positive comment about a certain movie or product. Okay. Okay. So usually for text classification, we can apply LSTM model. Here we also can decompose the model into two parts. You can see the orange part is somehow like an encoder. It could be LSTM. And the Y part is more like, it's a very simple operation, like a softmax operation, because we want to encode or we want to map the hidden representations of the sequence into a distribution over the category labels. Okay. For the dual model, it's in a reverse order. We first map the category into some sentiment embedding. That means we embed the model into some vector, and then we use LSTM to decode and generate the text sequence. Okay. So you can say we apply the methods on sentiment analysis. Here we show the results. You can see that we can reduce the error rate from over LSTM or dual supervised learning, and we can also reduce the perplexity of the text generation. So here is a summary. We propose model level dual learning with extended scope for dual learning, and we propose a new structure. The two models, they share the same components, but with different order, so that we can achieve model completeness, and we can cover different, both symmetric and asymmetric setting. Okay, so thank you. If you want to know more details, please come to our poster number 8 tonight.
So we don't have time for questions, so this concludes this session. Thank you.
Thank you.